Good afternoon, evening, morning, whatever it might be. We're going to take a look today at rotational inertia, and we're going to do a couple things. We're going to try to understand what it is. I'm going to describe a few facts about rotational inertia, if you will, and then we're going to learn how to calculate it for a couple of different kinds of objects. So first of all, some facts about rotational inertia. The first is what it's called. It's called rotational inertia. By some people, your textbook calls it moment of inertia. You may have noticed that. And different sources will give these two different names for the same quantity. That's unfortunate. I'll try to remember to call it moment of inertia from here on out because that's what your textbook uses. Other textbooks will use rotational inertia. So there you have it. Same quantity, two different names. Okay, what is it? I'm still not going to get into conceptually what it means yet. I'm going to say a couple more sort of just factual things about it. We have seen that the moment of inertia of a point mass is mr squared. Because that definition, I should say, came out of our analysis of the rotational kinetic energy of these 2 point masses going around a circle. And so this allows me to say something about moment of inertia, and that is that it's a quantity that depends on two things. It depends on mass, and it depends on where that mass is located. This is the distance from, what was it the distance from? Do you remember? It's the distance from an axis of rotation. So this is an important thing to recognize. Now, I'm going to also explicitly mention here, this is the equation for moment of inertia of a point mass. So this is something you would use if someone says there is a point mass 6 centimeters from an axis of rotation. What is this moment of inertia? Or something that you can treat as a point mass, whatever that might mean. So the important thing here is to recognize that moment of inertia is a quantity that is measured relative to some axis, a point. And it's going to be a point on a two-dimensional piece of paper. That's going to be where the axis is. And so it is incorrect to say, for a problem to say, there is a 3 kilogram ball, what is its moment of inertia? Period. It has to specify what is the moment of inertia of that 3 kilogram point mass relative to an axis. So they would say, okay, here's a 3 kilogram point mass. What is this moment of inertia? That's a meaningless question unless I also specify, oh, here's the axis of rotation, and this thing is 2 meters away from that axis of rotation. And it's going to rotate about that axis in, let's say, in the plane of the piece of paper. Nice circle, concentric on that axis, except that it isn't. Okay, so it's a quantity. The quantity includes mass and distance, and it must be specified relative to an axis. Let's just, for kicks, let's find the moment of inertia of this point mass, just to see what happens when you put the numbers into the formula. I put for this point mass, it is mr squared, and I would put it 3 kilogram times 2 meter quantity squared, and that gives me 12 kilogram times meters squared. That tells me the units for moment of inertia are units of mass times the square of units of distance. And right now that doesn't mean too much to us, but there is the moment of inertia of a 3 kilogram mass 2 meters away from an axis of rotation. Gee, that was fun. Okay, so the next thing I want to say about it is that we can apply this quantity to things other than point masses. I can't ask you what is the moment of inertia of an extended mass such as a stick. Oh, we'll be finding the moment of inertia of sticks soon enough. So here's a stick of mass m and length l. It could be a meter stick. It could be a other stick that's not a meter long. And I would say, oh, what's the moment of inertia of that stick relative to some axis? And so if I were to specify the axis as being in the middle of the stick, that means that this stick would be rotating about that axis, again, if I'm looking down from above and the stick is rotating in the plane of the board that I've drawn, or the piece of paper, then relative to that axis, the stick would have some particular moment of inertia. So the point I'm making now is that moment of inertia is a quantity that I can ask about for not just a point mass, but for something whose mass is distributed over space. The moment of inertia of this stick in this particular orientation happens to be, by the way, 1/12 times the mass of the stick times its length squared. Notice that in this case, this distance quantity isn't distance from axis of rotation. That is the actual length of the stick. I could also say, what is the moment of inertia of the same stick, but with the axis placed at one end? And so this stick is now rotating around an axis at one end, and I could say, what's the moment of inertia of the same stick, mass m, length L, but with the axis at one end instead of in the middle? And a funny thing happens, by the way, we'll see this soon enough. It turns out in this case that the rotational inertia is 1/3 ml squared. Same mass, same length, but a larger fraction, remembering, of course, that a third is more than a 12th. This, in fact, this moment of inertia is 4 times what the value is when the axis is in the center. Axis. So changing where the axis is located can have a significant effect on the value of the moment of inertia. I do recognize right now that we haven't really learned yet what the heck these numbers mean. As I said, we're just learning some facts about it. So again, to review, moment of inertia is called moment of inertia. It has to be specified relative to an axis, and it's a value that we can specify that we can use to describe either a point mass or an extended mass, like a stick, a disc, a ball, or even a llama if the llama is rotating. I guess the llama could be on a swing or doing gymnastics. Yeah, that's it. The llama's doing gymnastics. Think about that for a while. Google it, see what kind of pictures you get. All right. Okay, so finally, fact number 4 is, what the heck is it? What does it mean to say that the moment of inertia of a stick is 1/3 ml squared, and you put in the values and you get some number? Well, what it describes, so this is now the more conceptual, moment of inertia tells you, that's not grammatically correct, moment of inertia tells you the resistance an object has, I'm writing this down, has to changes in angular velocity. Okay, what does that mean? And so the rotational inertia or moment of inertia, if that's a big number, it means that an object has a larger resistance to changes in angular velocity. In other words, it's harder to make it have an angular acceleration. So I'm going to have you, actually right now I'm going to have you do an actual experiment. There's some demos that we'll be doing in class to try to demonstrate this to you. I'm going to have you try to do one right now watching this video. Take in fact, if you can go grab a lengthy stick, like a yardstick, the longer and heavier the better, within reason. But even if you take a pen or pencil right now, so if you need to, pause the video, go find a lengthy yardstick or a broom handle. If you have one without a broom attached, that would be awesome. But even a pen or pencil will work. So pause the video and turn it back on when you have that stick. Okay, so what are we going to do with that stick to find out what rotational inertia is? Well, here's the quick experiment I'm going to have you do. If you take this stick, if it's a pen or pencil, hold it in the middle. This is a really great picture. This is a picture of your forefinger and your thumb. So you're basically holding it between your finger and your thumb, balanced. So the pen or pencil is balanced. If you have a big heavy stick and you can't hold it between your finger and your thumb, put your whole fist around it and hold it up in the middle. Okay. Now, what I'm going to ask you to do is to not just rotate it, and you could twirl the stick the way I twirl a meter stick in class, but I'm actually going to instead, I want to emphasize the idea that you're going to give the stick some angular acceleration. So I want you to have the stick wiggle back and forth. So it's going to oscillate in front of you. And the stick can be held horizontally or vertically. And I want you to just wiggle it back and forth as fast as you can. But you're oscillating it, it's wiggling back and forth, and have it change direction as quickly as you can. And just get a feel for what that feels like. And again, if you have a big stick or a broomstick, put it in your whole fist and jiggle it back and forth as fast as you can. Okay, do that a few times, get a feel for it. And then what I want you to do is take the same stick, but instead of holding it in the middle, do your best to hold it off at one edge. So again, this is your finger and your thumb, or if you have a heavier stick, hold it in your fist there. And so now you're basically what you're going to do now is jiggle it back and forth as fast as you can, holding it one end. And if it's too heavy to do that, remember you can have it held vertically, so it's hanging from your finger and your thumb, and still try to, or if it's a larger stick in your fist, and try to jiggle it back and forth as fast as you can. And if you try this, you should have learned that it feels a lot easier in one of these situations or the other to oscillate this thing back and forth as quickly as you can. And if you try this experiment, I think you'll find out that it feels a whole lot easier to oscillate this rapidly in position A than it does in position B. This is true even if it's held vertically up and down, and you got your finger and thumb like that, and you jiggle it back and forth as fast as you can. It feels heavier when you hold it at one end. That's the best word you have for it. Even though the stick has no more mass, it doesn't weigh anymore, it's not heavier, but it feels heavier when you try to oscillate it like that. Well, what you're feeling there is the resistance this object has to change its angular velocity. When you oscillate it, every time it changes direction, which you should be able to get it to do a few times a second, a couple times a second, every time it changes direction, you're giving it an angular acceleration. You're changing the rotation of this stick. And so you're constantly accelerating it back and forth, back and forth, back and forth. And when you hold it in position B, it's got a lot more resistance. It's harder to get it to do that. Well, that's reflected in these numbers I gave you, and we're going to drive these in a second. That's reflected in these values for rotational inertia. When the axis is in the middle of the stick, we get this relatively low 1/12 times ml squared for the rotational inertia. When the axis is at one end, you get 1/3, 4 times as much. It's 4 times harder to oscillate this stick when it's held at one end than when it's held in the middle. So now you're getting, I hope, a feel for rotational inertia, what the quantity is, what moment of inertia is. This resistance that an object has to changes in angular velocity, angular accelerations. Okay, the next thing we're going to do is, I'm going to pause this because I've lost my recorder thing. Am I still recording? I'm going to try to pause this. There it is. Okay, I'm back. It looks like I have recorded everything so far, which is good. You know that because you've watched it and listened to it. Well, what I want to do now is a couple derivations. I want to come up with these expressions for the rotational inertia of a stick. And I'm going to do that on the next page, and boom, here I am on the next page. So the question is, what is the moment of inertia, of a stick? A thin stick. Okay. Obviously, I need to specify my axis of rotation, and so I have not yet specified a question. So I will then say, okay, I'll say, here's my stick. By the way, the thin stick means that its mass is distributed purely along its length. The height, if you will, from here to here is a much smaller value than the length of the stick from right to left, which I'm going to call L. And the stick has mass M. And I'm going to put the axis of rotation in the very middle of this stick. So this is my axis of rotation. It looks like I've sort of changed my axis. This stick might oscillate. The axis is vertical, and the stick might, if I were to rotate it, would rotate kind of into and out of the board. It doesn't matter because I'm not going to actually rotate the stick. I'm just going to specify where the axis is. And I want to calculate its rotational inertia, its moment of inertia. Okay, how do I do that? Well, I use the formula. But the formula that I have, the only formula I have so far right now, is mr squared, which applies to a point mass. And there's actually a very interesting calculation done in your textbook at the beginning of section 9-3, where they take the stick and divide it into thirds and treat each third as a point mass and come up with the moment of inertia. I think in that problem they have the axis at one end, but still, it's an interesting problem, where they basically treat this as three separate point masses. And actually come up with a value that's very, very close to the correct answer. Well, we, of course, will not stand for even really, really close. We need to get the exact answer for the rotational inertia of this, the moment of inertia of this stick. And so what I need to do is apply this point mass formula to this continuous mass stick. This might sound somewhat familiar because, oh, by the way, let me also point out that the point mass formula, if I have more than one point mass, as I did in the example in class with two masses on a string going in a circle, the total rotational inertia is the sum of all the mr squared products. And so I can do this mi/ri, and I sum over I. And there's some notation that I never remember exactly how to write. So I'm going to add up all the mr squared products. Okay. This might remind you of center mass stuff, because in fact what we're going to do is something very, very similar to our center mass calculations that we did a couple of months ago. And because what I want to do is say, gee, this stick isn't a point mass. It's got its mass distributed all the way from left to right. But I can turn into a bunch of point masses if I feed it through the calculus Cuisinart, which is exactly what I'm going to do. So, so here's what I'm going to do. I'm going to chop this up. The first thing I need to do is set up a coordinate system. And the coordinate system will be, in other words, my x-axis. And I'm going to have the x-axis, the origin of the x-axis, be located at the axis of rotation. That's important. And so then I'm going to chop this up into a bunch of little pieces. I'm going to feed it through the calculus Cuisinart, and I'm going to get a bunch, and I'm drawing 2 or 3 of them, of these little mass elements dm. And I'm going to then use this equation for moment of inertia of a point mass and apply it to this nearly infinite number of infinitely small point masses, each of them dm. So the first thing I have to do is take this formula I have for the rotational inertia of a finite number of big point masses and turn it into an equation for a nearly infinite number of infinitely small point masses. How does this change? Well, the summation becomes an integral. I'm going to add up a nearly infinite long series. And then my mr squareds, how does that change? Well, remember that I'm dividing this into a bazillion, a very large number of infinitely small point masses, and in each mass is infinitely small, and so my mass m is going to become dm. In other words, the mass of each piece is an infinitely small amount of mass, which means that I use the infinitesimal notation. It is dm. Does the r also get d'd? And the answer is no. Now, in this case, the r, remember, what does this r stand for? That r stands for how far is this particular piece of mass from the axis of rotation. So if I look at this particular piece of mass right here, this dm right here, how far is it from the axis of rotation? Well, it is this far from the axis of rotation. How far is that? Well, that is where it is located on the x-axis. That distance from the axis of rotation is the x value, the x coordinate, the x address of that particular point mass dm. So for this particular problem, my r, distance from the axis of rotation, becomes its position x on the x coordinate system, on the x-axis. So my moment of inertia formula turns into the integral of x dm, where x is the location of each point mass dm, and dm is each point mass. Okay, I'm going to be performing an integral to find the rotational inertia, the moment of inertia of this stick. Same rules apply as before. this is the integral that's been set up. Before I actually integrate a function, remember, I have to do the following. I have to get everything in front of the d whatever term to be either a constant, a variable, and I have to take this dm and turn it into d that variable. I didn't explain that very well. It's what we did earlier with center mass stuff. So in other words, x is a variable. So I have to get dm expressed in terms of constants, x, and dx. This is going to be very similar to what we did with center mass calculations, which is one of the reasons we did so many of them. And in fact, when we found the center mass of a stick, we did something very similar to this. So let's do that again. I am going to describe the mass distribution on the stick by saying that it has a linear mass density lambda, which is mass per unit length. And I'm going to say that the mass of each of these pieces, dm, this is a uniform stick, is equal to that linear mass density times the length. How far is it from one edge to the other of that little piece? And that length, of course, is dx. If you don't like the lambda, you can just write this as mass over length times dx. Okay, does that allow me to do this problem? And the answer is yes, because now I can write this as moment of inertia equals integral of x times dm, but dm, as we just saw, is lambda dx. I have satisfied this requirement. I now have expressed dm in terms of constants, lambda, x, I didn't even use x, and dx. So that makes me happy. Now I can perform this integral. I do have to come up with the appropriate limits of integration. In other words, over what domain on the x-axis are these variables, do these values have real meaning? In other words, where do these bits of mass dm fall on the x-axis? And they start over here on the left, and they go to here on the right. What are those values on the x-axis? Well, remember, the stick is centered at the origin, so the left-hand edge of the stick is L over 2 to the left in the negative direction, so this has a coordinate of negative L over 2. And the right-hand edge is positive L over 2 to the right. So we're going to start counting, start integrating at negative L over 2, and we're going to go to positive L over 2. So those are our limits for this particular orientation of the stick. And by all means, go ahead and finish this integral. It's a fairly straightforward one. The lambda gets pulled out, and I'm going to integrate x dx from negative L over 2 to L over 2. And that, of course, is x squared over 2, evaluated at negative L over 2 and L over 2. And that means that my moment of inertia is lambda times L over 2 quantity squared divided by 2 minus negative L over 2 quantity squared divided by 2. And we just have to be careful with all these fractions. Lambda times, let's see, L over 2 squared is L squared over 4. And pause.